Okay, good morning. So today I'm going to finish up this chapter on I/O systems and move on to file system interfaces, which is the next chapter. So this is where we left off last time. You send an I/O request and what happens. So this actually is an example from reading a file. Okay, so it does have to go through layers of the OS, and there's bookkeeping in the OS in terms of various control blocks. So, for example, file has file control block, process has process control block, and so forth. And these get looked up and mapped to the actual physical location of the sector. And then the driver takes over, translates those addresses into the lower level requests, goes over to the controller on the disk side, and then the OS just waits for the response to complete. And then once the data comes back, it needs to be put back into the form, put back in the right buffer, return control to the process. That's the general life cycle. So it looks like this flow chart here. And of course, the OS has to do a lot to make sure all the information needed is provided by the API and all the permissions is satisfied. So you access only if you have the permission. And then the device driver layer takes care of this and actually would set up the appropriate callback. And then when the device finishes, it comes back and then it triggers the interrupt service routine to do the handling. And remember, it could be split into two phases. First phase is to do just enough to acknowledge that the interrupt has been handled, but then it may have a second phase separately scheduled to complete the rest of the I/O or complete the rest of the processing. And otherwise, you might spend too much time in your interrupt service routine, which can be bad. Okay, and then the device driver has another piece that can complete the call and then return the control back to the I/O subsystem in the kernel and then return to the system call. So performance is an issue in I/O. It's impacted by various things, including how efficient your device driver is, the kernel I/O code, context switching time, how much data copying is there. We've seen the case of copy on write as a way to eliminate or reduce the amount of copying needed. But generally, you need to balance between the CPU scheduling, memory use, bus speed, and various I/O performance. And so in an inter-computer communication, what you have is more with a network adapter to network adapter. That's also considered I/O, even though it's not a device on the computer. And there you are sending some message from one computer to the next one, and it goes over the network as opposed to shared memory. So it's handled very much like I/O in the sense that you also go through the kernel down to the device driver, and then as part of waiting for I/O, you may need to do a context switch. And now in the sending system and receiving system, there is also the part that deals directly in hardware as well as in the software process corresponding to the hardware. And you may need to do a number of these switches so that it keeps these hardware resources utilized. And the kernel may have to do context switch between these. And the different controllers down below should have a certain amount of buffering so that it can tolerate some lag before it gets serviced. Okay, so that now to improve the performance of CPU, one of the things you do is try to reduce the number of context switches. And so we saw a little bit of a trick to doing that last time. Remember vectored I/O, just a quick review. So instead of sending one command corresponding to one system call, you batch them up. you take a vector. Vector, think of it as an array, okay? Like a mathematical vector is not just a scalar, right? It's multiple things. So think of it as an array of commands. And so one system call, one context switch, but then it does the multiple of these things, or at least it registers so that while in kernel it can service all these without having to switch back and forth between user mode and kernel mode. And there are other things you can do at the architecture level to shield the CPU from having to service so many different little requests. So front-end processor, terminal, concentrator, all of these things basically are on the user or client side that takes care of I/O locally without having to propagate every single keystroke, every single mouse move to the kernel. Okay, and another thing is to use these user mode processes or daemons to kernel threads so that the kernel can switch among multiple of these pending I/O requests without having to context switch back to a user. And so Telnet, you probably don't use Telnet anymore nowadays. You probably use SSH, but it's basically a server or a daemon process where you can connect from your terminal and use text mode to operate or to run a shell. And we saw reduced copying, like copy on write for I/O buffer. Although this still needs a little bit of work because you're actually remapping part of kernel space and relying on the address translation mechanism. And now to improve a performance I/O controller, one of the things is you can size the buffer or the transfer unit. And so DMA controllers a lot of times work with maybe 512 bytes. That is okay for certain things. But for much higher speeds, maybe 512 is too small. And so you may have to scale the transfers according to the speed. And DMA controller conceptually is outside the processor core. But nowadays you have these systems on chip, and then the same chip is integrated with many controllers, including DMA. But DMA still has to be attached to whichever I/O device you are doing. So maybe you have certain ports, it's attached to that port, or a certain bus, right? So there's still that interface that needs to be taken care of. Now, if your transfer size is small, then perhaps you want to consider polling, especially if the latency or the amount of busy wait is rather small, because there is still overhead associated with interrupt service routine, right? Because the processor does have to save state, restore state, in addition to registry. If you've seen code generated by SDCC, if it's a general one, it does push and pop, and on RISC processors that may be a lot more, right? So yes, the polling in some ways may be more efficient. So again, that's very device specific. And another thing is to make these devices even smarter. So put smarter controllers in devices. So like Ray controller is an example where it actually does quite a bit, and in terms of checking for the errors and how to recover, and that's all taken care of by the controller on the RAID side, not without burdening the CPU. Okay, so the device functionality progression has been your so if you want more flexibility, of course, you move things to a higher level, even up to application level, if not kernel level. But if you want to increase the efficiency, then you move things towards the lower level part, and so forth. So now this is still evolving, so it's not like there is just a fixed way or one answer to everything. This figure is taken from the book, basically showing the growth in both the capacity and the network speed. Okay, And so on the lower left corner, you have highest speed and the lowest capacity. That's the CPU and caches, although that's also increasing. And you have the DRAM and NVRAM, and they are slightly higher in capacity, but more in the latency. And now you have the storage devices, which are much higher in capacity, and then the latency is much longer. So what you might not be able to see very well is that center bottom here. If you can't read it, you can look at the book, or it says network latency. So that is a new trend in that, you've seen this cloud drive, right? So you have Dropbox, Google Drive. So you're putting storage outside, whether it's on a NAS or on a network drive, cloud drive type. And that is becoming feasible just because your network latency is getting shorter. And in fact, in some ways, it may even be shorter than your hard drive, or maybe similar to your NVRAM. Okay, so that and with a little bit of latency hiding or compression and others, it's becoming feasible. So that's the new trend here at the bottom, where you are relying more on the network to handle the storage. And of course, there's a lot of other benefits too, in that you can have storage that is managed for you. You don't have to worry about disk crashes, backing up, and things. And you can access from different places. Okay, so that is chapter 12 on I/O systems. And next is chapter 13. It's the next part in the textbook, which is on file systems. And it's divided into a couple of different chapters. So this is the higher level one. It talks about the interface to the file system. By interface, basically, what kind of call do you make, right? API, mostly. And then there's details in later chapters on how such a system is implemented. Okay, so these are a couple of topics I'll be covering. And so now a file, so what does it really mean? So from the user's point of view, you can think of it as a unit of data that you can store, or you can move or transmit. You can send to somebody as email attachment or over a text message, right? That's a file. It's a unit of some data. Could be a PDF file, could be an image, could be audio, could be any one of those things, but it's one unit. Now, that is different from something that is more like a container. So like if you have a directory or folder, that is a structure in maybe the file system, but if you want to send it, usually you have to zip it up, or at least the application program zips it up, or converts that hierarchical structure, preserve the structure into one file, and then you send that file, right? And from OS point of view, well, it's unit of some named data. So the file should have a name. And another thing that's important is it should be stored on some non-volatile storage. Okay, so that means it sticks around. The OS can count on once it's saved that it'll be available again, even if the OS reboots. And now there's the difference between logical versus a physical storage unit. So a file is conceptually, it's logically contiguous, right? So if I send you a file, you think of it as one unit, right? And then when you read or write, you don't think how it's ever broken up. And you don't even know the native block sizes or sector sizes, because it doesn't matter. Right? You're way above that level. Now, you talk about disk sectors, track, platter, only if you're talking about the physical level, right? So file is actually, even though as simple as it might seem, it sounds like just an array of bytes, and that is what it is. But it is actually an abstraction because to realize it, you don't always, in fact, most of the time, you don't always have contiguous physical memory or contiguous physical storage. The file system has to take care of that for you. Take care of taking pieces and string them together to store that file. Okay, because that's from the OS's point of view. It has to make use of some non-volatile storage, and that way the user doesn't need to think that there is all the physical consideration. Are they really linked together? Which location does it link to, and all that. But that doesn't mean the file system has to do a lot of this work. I mean, it doesn't sound like very complicated, but there's quite a bit it has to do. And so now file to the user really means the content itself. And the user may think of these as typed data, even though OS may or may not consider these as different typed data. So the user may think, oh, this is text file, this is source file, this is executable file, this is PDF, this is JPEG, and all that. OS may or may not care about the type. Now, associated with the file are attributes. So some parts are or may be exposed to the user, other parts may not. Okay, so file has to have a name, and otherwise it's data. And this is true whether you're talking about the OS or the user. And the name had better be human readable string, and the name is not part of the content. So you can change the name without affecting the content. And in the file system, in addition to the name, there is a file identifier. So think of it as a number. Okay, just like a process has a process ID. File would have its unique tag, and a tag here really means just an integer. And why have this kind of unique tag per file? Well, because you can create different what's called links. Later you'll see links. That is, the same file may appear in different places, different directories, or as different names. So name is just one way of getting to the file, but it's not necessarily a unique way to get there. And so but then identifier has to be the same. The type may or may not be an attribute, and so for systems that support different typed files, yes, then it would be an attribute. Nowadays, it's probably not as common, but or they might not support every single type because there's just a lot to track of. But for a while, that was actually done for good reasons. So, like for example, first Mac, it actually is all the files are typed, and these typed attributes are stored separately from the content of the file, and you can edit those separately using a different tool. Now, location would be a pointer to file location on device, and these could be specific, like the sector platter and all that. The size, now you could figure out the size by, well, I mean, you have to interpret the data. Because if you don't track the size, then all you have on storage device are these sectors as basic units. And if not enough, then one links to the next, it links to the next. But where do you stop? And even if you link to the next, how many bytes in the last sector do you occupy? Well, you don't know. So the size has to be stored as a separate attribute. Okay, and the current file size in terms of number of bytes or number of words. Word would be the native CPU size, like the registry. If it's 32-bit, then words would be 32-bit quantities. Or number of blocks, or maybe there's a limit to the maximum size that's allowed. And also, file attributes may have protections, but these may or may not be preserved while you transmit the file. So these protection attributes control who can read, write, and execute. Now this who is up to a separate definition because just how do you track identity, right? You can't really say this particular person, right? So it would be in some user namespace or some other group ID. That's all you can do.
size 有办法在 user 的 interface 上改变
No, a user interface you can think of it as a shell, right? And depending on what API that shell calls. So if it calls an API to change the size, sure, why not? But most user interfaces don't support just changing arbitrary size because that does bad things. But you can imagine writing a command you can launch in shell, and that's very easy because you can just I'll talk about file API, and then you can seek to a certain point and then just chop off the rest of the file. You can certainly do that. Okay. Now, in addition to this, these attributes on access information, so for example, the timestamps, user ID. So in fact, there's more than one timestamp, right? So that could be time created, time last read, time last modified, time added, and all that. And user ID would be data for protection, security, maybe even usage monitoring, accounting. So these attributes, where are they kept? So these attributes are kept in a directory. So that means if you transmit just the file content without the directory structure, you may have you may lose a lot of these attributes. If you want to preserve these attributes, what you end up doing is you then zip up the file along with the directory that contains it. That way, it makes sure all these additional attributes, besides the file content, get preserved in the enclosing directory. Right? So zip, what it'll do is it not only preserves the file itself, but also if it's in any directory, it also reads those associated attributes with the file in the directory so that they get put into one file. Some people call this serialization. And if you do zipping, then it also does some compression as well. And in addition, the metadata may include things like checksum, sometimes like MD5 hash, other things, so that because nowadays you do a lot of transfer over the network. When you do a transfer over the network, your connection may be lost. You may get partial file instead of the complete thing, or maybe you have to combine several pieces because each one may have a maximum size. And anytime you do any kind of transfer or splitting up, concatenating, you run the risk of corrupting something. Right? So having a checksum is useful because then you can check after you assembled the whole thing, is it still consistent with the original checksum? Okay. And Windows has this mechanism called Registry. And that is one place where some of the metadata file is kept. Metadata is kept in Registry, and then you use a special tool to edit that. And this is an example the book gave on Mac OS. So it does have extended file attributes, and that includes a list of apps that can open the file. And some of these may be determined by the OS rather than being carried around by the file. It could be based on the file extension, so the .3 or 4 or more letters of extension. And in fact, if you download from the network using a browser, it may even save the URL from which you downloaded from. And in addition, there's user labels. You can label in different colors or importance and other things. And the file may have also an icon. So in this case, is a LaTeX file. So it looks like a text file or editor file. And it may not be directly carried around with each instance of this type of file. Maybe it is defined in the app itself. So the app would have a path. and then this may be just a link to that. Okay, and another attribute may be the file's checksum. Okay, but as you transmit this file, so you drop it over a text message or upload to say a cloud drive, some of these attributes may not be transmitted. May be lost, or you do email attachment, just because you're only transmitting the file content part plus its name and its size, nothing else. A lot of these other attributes may be lost. Okay. Now, so open file attributes. This refers to the attributes associated with files that have been opened. Okay, so that's what open file attribute. So open in this case is an adjective, it's not a verb. Open file, so that's files that have been opened by your API call. So remember, you can do open and then the name of the file, right? You get a file handle back. So after you open the file, there's additional attributes put in by the OS for the file that's opened. And these attributes are divided into those per process as well as the system level, okay, system-wide across different processes. So each process, remember back in the days of these process control blocks, one of the tables in there is the open file table. That is a table that tracks which files have been opened by this process. That's what open file table is. Okay, it keeps track of which files are open. And this can be useful in many different ways. One is, say, if you're running a process that has a few files open and you try to delete a file, what happens? A lot of times you get an error message or warning message saying, sorry, I can't delete this file because some app is using it, right? Some process is using it. Yes, so that's what it can do, and it can track you by this per process open file table. And each open file would have a file pointer. What does that mean? So that is, remember when you open the file, read and write, there's this concept of the file, you might call file pointer, that is the current location within the file. So when you first open it, that file pointer points at the beginning, 0th byte, right? Think of it as big array. And then as you read or write, it gets advanced. And then, so it gets incremented for every byte or every unit you write, right? So that gets moved along. But you can also say, well, I want to go back to another part. You can do kind of random access. And the way you do that is by calling seek, S-E-E-K. That moves that file pointer to a different location. Okay, you can rewind it all the way to the beginning and reread it. That's fine too. Or you can skip all the way to the end if you want to just continue writing to the end, appending. And also per process file attribute would include access rights. That is per process access mode information. So this is interesting because you might say, wouldn't I just want to have that be at the per user level instead of per process level? Well, that may be the case, but yes, you could actually control whether you want this, the process launched by a user to have different access rights, just depending on how it's launched. And this may be useful for cases where you have a server and you run a sandbox. You want to limit, so for example, you want to access a file, want to access a, say, web server. And the web server is always run as one process, one user, unless you specify a different way to launch that. But it's the same user. But depending on who's logged in, you might want to give them different access rights. So even though the server process runs as always this, I don't know, a web server user, right? Depending on who's logged in, right, over this session, you may change their access rights, or you may run it in a sandbox, right? So that's why it's a per process type of access rights. Now, OS-wide attribute open file attributes would include the open file count. That is, so the same file may be opened multiple times either by same process or by different processes. Okay, and that's done very commonly, especially for read-only type of files. Even program executables are like that. Okay, so you do the count. Every time somebody calls an open, you increment the count, and so then that you keep track of how many processes are currently accessing this. And when the last process closes that file, count becomes 0, then the OS can remove that entry from the system-wide open file table. And another would be the disk location of the file. So again, this is for the OS to track where to put the file. And in fact, the OS may move it physically without logically moving it. And it may also do some caching. That is, to keep track of the file if it's used a lot, or you can do prefetching. It caches it, and this is OS caching, not processor caching, right? So OS allocate some kernel buffer to save a cache, so that next time you read, you don't always go to memory, or you don't always go to file system, you don't always go to disk. It always can check, is it a cache hit? And this is done in software. If so, then it just takes it from its own memory buffer. So operations, and that's really the topic for this chapter. You have create, write, read, delete, truncate, open, close. Okay, you probably know what these mean. Create to make a new file, write to write at the current location. Excuse me. And you can potentially move it. And reading to read at the current location. And then the fourth one, that's seek. That's what I talked about. You can move the file pointer to any location you want, relative to beginning, relative to the end, with an offset, positive, negative offset, or to relative to the current location. I want to move forward by so many bytes or backward by so many bytes. Okay. And delete will be to delete from the directory. Okay. Now say, okay, does the file continue to exist after I delete from the directory? Well, it depends, because remember there's the concept of linking. So if it appears multiple times in different directories, then it better stick around until the last directory deletes it, right? So if it's deleted from the very last directory that contains it, then yes, it can be reclaimed. But does the OS delete it right away? Depends, right? So you can imagine maybe some API forces real deletion on the spot, or other times it may just stick around, and OS may do kind of lazy evaluation, doesn't really delete until it has to, or does it in the background. That way it saves some time, so it can be more responsive to the user. Now, truncate would be to take a file that it already exists, but then write over it instead of doing a new create, instead of deleting and creating. That way, it's more efficient because the record or all the attribute fields have already been allocated. In fact, there's already certain file blocks already linked, right? So that way, the OS saves the work of reallocating these metadata attribute space, and saves the work for allocating these new blocks for it, because it's just reusing the existing one of the existing file, but you write over it. Okay, so that way, updating is much easier than creating a new one. Open, which means you have to do it in the context of a directory, current directory or a given directory. Search in there by name to see if you can find it. And for reading, yes, you want to find it. For writing, well, you might think twice about whether you want to create it or you want to override it, right? But that API is different from the lower level opening. Opening at the lower level really just means you want to find an existing one to open. The user level open actually includes a number of things. Could be open for reading, if not for writing, or for creating, for truncating, right? That's all combined in one open call. Close would be well, one is to decrement the open count. Another is to flush out any potential changes you have made from any buffer it has, and then flush to the disk structure and update these attributes. Okay, so now a file, it can be shared by multiple processes. And just as with memory sharing, you may want to use a semaphore to lock it. With files, you want some locks as well. And now these locks would maybe not be implemented using semaphores because it's not necessarily just a memory structure. But OS has to implement different mechanism, but the idea is similar to the reader-writer kind of lock. And there's locks, so shared lock would be similar to the reader lock. So that means as soon as you start having one reader, you allow additional readers to also open that file for reading. But if some writer attempts to write to that file, maybe it should be disallowed, right? So that way you don't get surprises. In the middle of reading something, suddenly the file content gets changed, right? So that's one form of lock. Another lock would be exclusive lock. That is, at most one process can get that lock. And so that way, so for example, one writer may block out all other writers, right? Because otherwise it wouldn't make a lot of sense for different writers to be writing to the same file at the same time. They lock each other out, okay? And now these locks may be what's called mandatory or advisory. So mandatory means that when you lock it, there's no other way around. It's just, it's strictly enforced. Whereas advisory means when it attempts to do it, it gets an exception, but only within the process. So it's not a drastic thing. It doesn't involve context switching. It's just a little bit of a checking status. And the process can do this as a slightly lazier way than checking the attribute first, right? It just goes ahead and attempts to access. But if it fails, gets an exception, and then decides what to do. And if it really wants to, maybe it could just go ahead and do whatever it wants. But that's not recommended. Now, file types could be in file attribute. And so now the app itself may say, okay, this is a type that I understand. But an app may understand multiple types of file. So for example, you take Microsoft Word. It opens docx, maybe even HTML, maybe even, I don't know, it opens a number of different files, right? So it's possible that you set the creator attribute, but then you don't tell it what exactly what type. And then the app itself can figure out based on the context. By reading a few bytes or maybe reading some header, by parsing a little bit, then you say, oh, I understand this is one of the different files. So even if you don't rely on the file extension like .doc or .docx or .html, maybe it can figure that out. And so that's often what happens. So the creator attribute mainly is for the shell or user interface to pick which app to launch. Okay, but there are other types. If you know the file type, then the shell can do something different, which is saying, oh, well, this is a text file. And I know there's at least 5 or 6 editors that can edit text file, plain text files. So it may present you with a choice of these apps that know how to open. So this, again, very OS-specific type of thing. Now, so file types, in some cases, may be part of the format of the file. So a lot of files have what's called magic numbers, And these would be some unique, you might call string, but really just sequence of bytes that define some kind of signature. And so at the beginning, especially for binary files. And so you see that in these like compiler generate these object files. So like partially compiled or compiled but not linked, these files, or some audio files, or if you look at PDF files, you actually see some, maybe not magic number, but at least some signature there at the very beginning, and then you see some garbage following that. Yes, that there's some magic going on. Okay, and image, audio, a lot of them. Huh? It's basically it says this is a unique sequence of bytes that other types are unlikely, almost impossible to duplicate, and that's what identifies itself as a file of a certain type. Okay, so Unix has a command called file, which is a rather creative name, but in shell you can just type it in file and then the name of the file. It'll try to guess what it is, and how can it guess it? Well, it tries to parse the file a little bit. Okay, if there's a magic number, looks in its database. Oh yeah, I understand. This is an image. This is PDF. This is what. Or if it's a .c file, well, it tries to parse it and say, oh, this looks like C source code to me, or this looks like Python to me. This looks like shell script to me, and it may make a number of intelligent guesses, also based on file extension. So try it out. On most Unix shells, it's a pretty useful command. So it really is based on a number of different things that both OS specific as well as extension and magic numbers. So here are just some samples of file types and the usual extensions. So executables would have like exe on Windows, .com for DOS, and .bin for some other, or .app on Mac, and a lot of Unix ones don't actually have an extension for executables, but they would have this magic number in front. Object files would have .o, .obj, or .rel, all these, right? Source file, for the different language, or .asm assembly, and then batch files would be like shell scripts. Different markup language, HTML, XML, word processor, library, and so forth, right? So yeah, from the file name, you can actually make good guesses of what it is, but somebody can just arbitrarily name their file with these, and so it's better to check the content. Now, file structure, most of the time, it always just treats them as just raw bytes, okay? But in some cases, OS may support some simple structure, or may treat some separately. So text files could be treated separately. So the assumption is you have certain lines, and then these lines may be variable length, but you have certain sequence for your new line. So either like DOS, Windows would be 2 characters, right? See character return and a new line, and a line feed, and whereas with most Unix, it's just a new line. And it could be variable length or fixed length. OS usually doesn't get involved in this detail, because if you do any more than that, it's really just a simple database now, right? So, and some could be complex structure, but these are handled by the app. So for example, if you take a Word document, I mean, do you even know what's in there? If you try to look at it, well, it's a lot of binary in there. In fact, Microsoft has been keeping the format or structure of all these Office documents is secret, making it nearly impossible for other companies to reverse engineer and make a clone for their Word or PowerPoint. But people over time figured it out, and Microsoft has been a little bit more open, still not completely open. Anyway, and so some of these may actually contain a zipped up structure for an entire directory inside. Right? It could be anything in there. It could be arbitrarily complex. And so in any case, the OS or application may decide on the file structure, but most likely it's the application, because otherwise your OS can get really complicated and for no good reason. Now, access could be sequential access or direct access. Sequential is just like what we usually do with text file. You open, read, and then it moves the file pointer to next, or right. It also advances. And reset, you can rewind it to beginning, or you can seek to the end. Direct access would be you would read end or write end or position to end, and you would read next record or write next record. So Unix file API does include reading or writing in some size, although it basically just treats these as a generic pointers, a voice star type of pointer, and then but you have to do a casting of structure. So you superimpose a struct on top of it, but you can simulate something that's like a record access.